Hello and welcome back to Complex Analysis. We've already reached part 30 in the series, and today we will talk about the important identity theorem. In a rough sense, it tells us that if you know a holomorphic function on a small subset, you know it everywhere. So you see again, the term holomorphic is very restrictive, very strong. However, before we formulate the theorem, I want to thank all the nice people who support this channel on Steady via PayPal or by other means. And please don't forget to download the PDF version and the quiz of this video with the link in the description. Okay, now before we formulate the identity theorem, let's first recall what we already know. For this, let's consider a holomorphic function f with domain C where we fix the values on a given circle. In other words, we know how the graph looks like when we restrict the function to the circle. This means we know all the pairs z, f of z, where z now lies on the boundary of a given disk. So as always, we have z0 as the middle point and r as the radius. Okay, and now we assume in addition that we have another function g, which is also holomorphic, defined on C, and should have the same values on the circle. More precisely, the graph of both functions should be exactly the same when we restrict them to the boundary of the disk. And now we can recall Cauchy's integral formula, which tells us that the values on the boundary of the disk already determine all the values inside. Which means the two functions f and g actually coincide. At least we know they do it in the disk. In particular, there's only one holomorphic function inside the disk that has exactly these values on the boundary on the circle. And now exactly this fact the identity theorem will generalize. In fact, the identity theorem will also tell us what happens outside of the disk. And for this reason, we are also allowed to choose a general open domain for the domain of both functions. So as before, we have again two holomorphic functions. And as I said, D should be an open domain, so an open set, which is also path connected. Indeed, this is important. The domain is not allowed to consist of two unconnected parts. Okay, so these are the two assumptions we need to describe now two equivalences. So first we look at a set where both functions f and g coincide. So more precisely, we have the set of all points z in the domain D, where f of z is equal to g of z. Now, this one could be a small or a large set in D, before it was just a circle. In fact, it does not have to be large at all. The only assumption we put in here is that it has at least one accumulation point in the domain D. So this is one point in D that has a lot of neighbors that lie in this set. Okay, and now the surprising fact is that this is actually equivalent to f is equal to g. So in other words, one accumulation point is enough that this set is already equal to D. In other words, this small set already determines the whole holomorphic function. So you see, this is a generalization of the fact from above. However, we can also put in a second equivalence here. This is now the statement that we find a special point in D, which we call C, at which all the derivatives of f and g coincide. And we need this equality for all natural numbers n including 0. So you see, this here means if you consider the Taylor expansion, the power series expansion of both functions, they coincide at this given point. Hence, you also already know they coincide in a neighborhood around this point. And indeed, this is also enough to conclude that f is actually equal to g. Okay, and now this whole thing here is what we call the identity theorem of complex analysis. Okay, now before we prove this fact, let's first talk about the important concept in this theorem, the concept of an accumulation point. So in order to apply this theorem, you actually have to know what an accumulation point in D is. Therefore, let's write down the definition here. Okay, so we take a point P in D, and it is called an accumulation point of the set M, where M now can be any subset in D. So the first thing to note here is that the notion accumulation point is always with respect to a given set. And the second thing is that the point P can be an element in M, but it does not have to be. The only thing we need is that it has a lot of neighbors lying in the set M around it. And you should know this notion of a neighborhood we always describe with open sets, or also sufficient we describe it with open epsilon balls. So we just consider all open neighborhoods of P, so all open sets U, where P is an element of U. And then what we want is that U, without the point P, still has elements of the set M. In other words, the intersection with M is non-empty. Okay, so there we have it. This is the notion of an accumulation point for a set, and it's always important if you want to form limits. Therefore, this term occurs a lot in different branches of analysis. Here in the complex plane, it's not so hard, the visualization is very clear. However, I would say to get the correct idea, let's look at some examples. For the first one, I want M to be the natural numbers. There we know, in the complex plane, this looks like a chain of points. Therefore, we immediately recognize that this set has no accumulation point in the complex numbers. So for example, this point here can't be an accumulation point of the set M, because if we choose such a small epsilon ball and remove the point P from the ball, then nothing remains of the set M. And of course, this argumentation works for every point in the complex plane, because you just have to choose the epsilon ball small enough. However, still, it can happen that such a discrete set has accumulation points. So for example, this set 1 over n accumulates around the point 0. This means the point 0 here is an accumulation point of the set M. Here please note, 0 is not an element of the set M itself, but still it's an accumulation point of the set by this definition. Okay, so we have this cleared up, and therefore now we can talk about the proof of the identity theorem. However, I want to keep it short, therefore I just give you the correct ideas without all the details. In fact, the first idea is already the best. Instead of considering two functions, just consider one. And as often, this can be done by considering the difference of both functions. This works because we still get out a holomorphic function. And then we just have to show the equivalence of three statements. Now, these are the three statements from above, but now formulated for the function h. So please recall, the first statement was that this set M here, where f and g coincide, has an accumulation point in D. And now we can reformulate that for h, which means this is a set where h is 0. And now this set of the zeros should have an accumulation point in D. Okay, and then the second statement was that f is equal to g, which now means h is equal to 0. In other words, h is just the 0 function. Okay, then finally the last statement was about the derivatives. And with the reformulation, it reads that there is a c such that all the derivatives of h vanish at this point. Well, now you see, we just have to prove three implications. And I want to start with the one that assumes the first statement and shows the third one. More precisely, what we will do now is to use the contraposition, so we assume not 3 and will imply not 1. So we see not 3 means we don't find any c such that all the derivatives vanish. More concretely, it means that for each point c in the domain, we find a minimal number m such that the mth derivative of this point is not 0. However, now from the last video, you know that each holomorphic function can be represented by a power series. In fact, it has to be the Taylor expansion at the given point. So in this case, let's write h of z as a power series. And actually, this power series now can start with m. This is simply because in the expansion we have the derivatives as coefficients. And because we chose m minimally, we know all the other derivatives before m will vanish. Okay, so now this is our function h written as a power series, which is correct in a neighborhood around C. Or more precisely, as always, we have it inside a disk. Hence, this equality holds for all points z inside such a disk. Okay, but with this, now we can conclude that very near around the point C, this function is not zero. To see this, maybe let's call the coefficient here in front ak. Therefore, the first and most important part of the series is am times z minus c to the power m, plus the whole rest, which has a higher power in z minus c. This means this can be made very, very small if we are very close to c. Moreover, we also know that for the first part here, the coefficient am is not zero. Hence, if z is not c, the whole function h of z is not zero. And indeed, that's all we need here. We just need one small neighborhood of c, which we call u. However, this now means that our set M here, which consists of the zeros of h, has no accumulation point. So you see exactly what we wanted to show. So if we write it down again, u without the point c intersected with M is equal to the empty set, because we know that h of z is not zero for all z that are not c. And with this, now we know c can't be an accumulation point. And this argumentation works for each point c we choose in D. Therefore, there are no accumulation points of M at all. Okay, then I would say, let's go to the next implication. Now we go from statement 3 to 2. Now, for showing this implication, one considers closed and open sets. First, I want to define the set AK, which should be a closed set. It's the set of all the points z in D, where the kth derivative of our function h at the point z is 0. Now, this has to be a closed set, because this function here, the derivative, is a continuous function. And this here is the pre-image of a closed set, just one point, and therefore it needs also to be closed. And now if we define a new set A, given as the intersection of all these AKs, then this is also closed. This is a general fact: an arbitrary intersection of closed sets is always closed. Now, if you're not familiar with these terms, with closed sets and the relations with open sets and so on, I would say it's not a problem at all. For the moment, we just need it here for the proof. However, if you want to learn more details about this, in my manifold series and my functional analysis series, we talk a lot about this. Of course, we do this as a foundation in the beginning of the two series. Okay, but let's continue here. Here please note, this set A consists of all the points where all the derivatives of h vanish. Hence, by assumption, we know this is not the empty set. This is exactly our assumption given in statement 3. Moreover, now we can also show that A is, besides being closed, also open. And there you might already guess, this works with our power series expansion again. Because now if we choose a point C in A, we know that the coefficients of our power series vanish. However, we know that this expansion works in the whole open disk around the expansion point. Therefore, if we choose a point in the disk, we know that also there all the derivatives will vanish. In other words, the whole open disk lies also in the set A. And this is exactly how we have defined the notion open at the beginning of the series. Okay, now we have a set A that is open and closed at the same time. Indeed, this can happen, but because D is a connected domain, this is only possible if A is the empty set or the whole domain. So in our case, A has to be D. Indeed, this is something we can easily show if we assume that D is path connected. However, as promised before, I want to skip some details here and just give you the general idea of the proof. Therefore, I think this is fair enough. Now we have shown that A is equal to D. In particular, this means that H can only be the zero function, which is exactly our statement 2. Okay, then finally, the last thing we have to show is that we can also go from 2 to 1. However, this is trivially true, so there's nothing to show here. Okay, with this our circle is closed and our whole proof is finished. So in summary, we have proven the identity theorem for holomorphic functions. And in fact, this one has some nice implications for all new holomorphic functions we want to define. So we know if we know the function on a small set just with one accumulation point, we already know the whole function. So for example, there's only one holomorphic function that when we restrict it to the real number line is the signed function of the real number line. So there's no other way to extend the well-known real signed function to the whole complex plane if we want complex differentiability. And of course, this holds for all extensions of real functions to the complex plane. Okay, with this idea in mind, I would say let's discuss it in the next video. So I hope I see you there and have a nice day. Bye.